Hi everybody. We're going to present about the simulation of the diffusion of chloride ion in reinforced concrete exposed to a marine environment. Reinforced concrete is a concrete in which the steel is embedded in steel and the two materials act as resistant forces. Corrosion is one of the main causes for deterioration of reinforced concrete structures in the world. This is one of the reasons why industry must invest great amount of money in repairing and giving maintenance to public and private constructions. One of the main reasons why corrosion occurs is due to the penetration of chloride through the network pores when the structures are in marine environments. So what is our objective? Our objective for this project is to calculate the chlorine concentration profile in 50 years of different depths through several concrete mixtures to determine which will avoid the corrosion and decrease the concentration of chlorine through the mixture. The geometry of the pillar is of most importance. We will compare cylindrical geometry to a rectangular prism using the same dimensions, that means height, length, and depth, to see which case has a lower diffusivity. Based on the paper, 5 different mixtures of reinforced concrete were chosen for the experiment: H1, H2, H3, H4, and H5. The ratio of each fine aggregate and coarse aggregate are as shown below. The relationship between cement content per unit volume shows that H2 has the greatest mass per unit volume. This directly affects the water-cement ratio, which is the porosity, to be the lowest. This tells you that it will be harder for the water to go through the pillar. The paper that we searched showed many results of diffusivity depending on the saturation degree. We chose a saturation degree of 100%, since this will have the higher diffusivities due to the excess in chlorine, and this value is reported for every mixture. We're going to show you a graphical representation of our problem. We have a pillar in a dock that will be in constant contact with seawater. Chlorine will provoke corrosion with time, and we want to calculate concentration profile inside the pillar. We chose 50 years because diffusivity in solids is too small, so to be able to see a big change, we searched the useful time of a concrete pillar, and it was of 50 years approximately. Okay, so now the assumptions. We had to take into consideration many assumptions for our system. One of the most important is that the concentration at the surface is constant because it is in constant contact with the seawater, and the salinity is an average that remains the same. So the concentration of chlorine in contact with the surface will also be the same. Besides that, the bases of each pillar are isolated, so the top of the pillar is not in contact with the water, and the bottom is buried in the sand, so we can neglect those bases. For both the cylindrical and the rectangular prism, we consider the same height, depth, and length. However, the area slightly changed. With this measurement, the x1 has the same value on both geometries. So, what was our approach to solve this problem? With the following equations, we calculate the parameters xd, which is the relative time, the n, the relative position, m, the relative resistance, and Ya, the unaccomplished concentration change. This is an example of how we calculated the Ya. Once we get the xd, you can go to the graph either for the cylinder or the slab, and then you calculate Ya. We calculated all the concentrations of A in 4 different depths for both geometries. We did this step for every mixture. So what is the solution for our best mixture? We made a graph to compare the concentration of chlorine at different depths in both the cylinder and the rectangular prism. As it can be seen, in both cases the mixture H2 has the lower diffusivity, meaning that it is the best mixture for us, since the best case is to avoid corrosion due to chlorine. The H2 mixture is the best mixture since it has the greatest ratio of mass of concrete with respect to volume, and the lower porosity. These two aspects make the diffusivity to be the smallest and therefore have the lowest corrosion. So we now know which mixture is the best, but we also need to identify which geometry is the best. By comparing both concentration profiles, we can see that the rectangular prism has an even lower diffusivity in comparison with the cylindrical one. This may be because the surface of the cylinder will be equally apart from the center at any point of the surface, while in the rectangular prism you have edges, so the distance will vary as you get farther away from the center. This will cause the concentration to take longer to reach the center of the pillar. In conclusion, we can say that our result is very viable because it can be applied to avoid corrosion and calculating the useful lifetime of pillars in docks. The physical meaning of the result tells us that the best mixture for us will be the H2, since it will have a lower diffusivity inside the pillar, and the best geometry to avoid corrosion will be the rectangular prism. The application to other areas may be the cost of the geometries. You can evaluate how much it will cost since you will have a different area and a different volume. Also, the resistance of the pillar will be related to the geometry of the pillar. You can apply the same idea for bridges and maybe use another material such as metal. The learnings in this project is that there is a strong relationship between the geometry, the diffusivity, and the corrosion. And the difficulties of this project were identifying the parameters of the system itself. And that's it. Thank you very much.